Okay. So again, we're going to be working through all the practice quizzes, and then practice exam and exam. And we're going to try to get through all the important stuff that we need to know for exam 2. And hopefully we can get like a decent review in. So I have practice quiz 1 open right now. So the quiz from 2019. So what I'm seeing from question 2 on here is definitely the pink sheet. Just remember that you have to memorize that pink sheet again real quick. It's not too much. Just remember like the word concerted, the word, like specific first order versus second order, that kind of stuff. Just remember all that. So I won't really go into detail with that because that's just something you need to go memorize again. Okay, so there's this question in the beginning, which I guess we can go over. So it's saying which one is going to react most readily with HBr. So there's a few different alcohols, basically. One of them looks like this. There's an OH here. And then the other one is just like this. And then another one is like this. So Mubaraka, what do you see as the differences between the 3 of them?
3 degrees, 2 degrees, and 1 degree.
Yeah. This is primary. So basically there's a tertiary, a primary, and a secondary alcohol. And so for the alcohols, for alcohols, by the way that some people might look at this and say, well, no, they all look, it's about the carbon that they're attached to. So the alcohol itself is attached to this carbon. Now this carbon is only attached to 1. So that's what makes it a primary, okay? Whereas with like the other one, like the tertiary one, this alcohol is again attached to a carbon, but that carbon is attached to 3 other carbons. So it's about the carbon that the alcohol is attached to, is that tertiary. It's exactly the same as with bromine and stuff. So when they say reacting with HBr, I'll just remind you of the mechanism again. So Mubaraka, there's 3 of you in the room right now. I don't know what's going on, but okay. So I'll just remind you of the mechanism of how OH reacts with HBr. So we have an OH there, and we have HBr. This is one of the first things you learned, I think. So basically, the OH here reaches out and grabs an H from the HBr that breaks the Br off. Then we get one with H2O, right? And then H2O is a good leaving group, so it's going to protonate. Depending on whether this is SN1 or SN2, I'm just going to go ahead and make this SN1 because that'll make it like easier for us. So it protonates, and then you get a carbocation. This is again SN1. If it had been SN2, then you would have like you wouldn't have that carbocation intermediate. So what happens after this is that your Br is gonna come in with its negative charge and just attack the positive charge of the carbocation. And then what you get is you just get that same structure, but instead of where the OH was, you have a Br now. And I suspect you may be asked to do this mechanism on the exam, on the final exam. So definitely like try to memorize that. And then going down to the bottom of the page, I'm seeing now that they're just asking you for that exact mechanism. So you might have to do the mechanism. You also might have to do the energy diagram. For the energy diagrams, I don't really think there's much use to me going over that because it's just something that you have to memorize. But essentially with energy diagrams, it's about how much energy does it take for each step to happen. And what I would recommend knowing though is like what are the steps that require the highest energy to happen. So in the practice quiz, the last question, question 3, or the last question of the first page, is asking you whether this is going to be an SN1 or SN2 reaction. We see that we're dealing with a tertiary alcohol, so we know that it's going to be what, Julie?
SN1. It's going to prefer SN1 because SN2 requires a backside attack. And right. There's like 3 random methyls that are blocking the backside attack.
And it's not only that, it's also that tertiary carbocations are more stable. That's more what it is. Because we know like tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations. So it's more about the fact that you're never going to find this in real life.
I mean,
where
yes, that's
this is
also
very,
true.
yes, yeah. So this is very likely to happen, which is also just like a quick thing that's good to remember. So, going back to this whole mechanism, so he asks you whether it's SN1 or SN2. We're going to choose SN1. And then after that, he asks you for the mechanism, which I just showed up above. But also after that, he asks you for an energy diagram. And so you just need to draw your energy diagram. And so for SN1, it's a little bit more like involved because it has that carbocation intermediate. So it starts out something like this, and then it goes like this, and I don't know, something like that. So basically, one thing that I would recommend, oops. Okay, so one thing I would recommend, no. It's more like, okay, sorry. So one thing I would recommend knowing though is what is the highest peak? This peak right here. So the highest energy is what it takes for the from the OH or the H2O to leave. This takes a lot of energy for it to break off. Okay. So I'd recommend knowing this diagram in and out for sure. You need to know all the steps and how to draw them. And you usually do dotted lines for showing that things are leaving or attacking. You also need to know the diagram for SN2, which is, again, it's a little bit more straightforward than SN1 because it doesn't involve that carbocation intermediate. So you need to know both of those. You do not need to know an energy diagram for E1 and E2, as far as I know. Okay, then he's saying, but you should know that, E1 is like similar to SN1 in that there's a carbocation intermediate. E2 does not have a carbocation intermediate. So then he's asking which of the following is the best leaving group. This is something you guys know very well now because remember that list he gave you guys recently where it had like, it had like it had OTS, it had like, yeah, OTS is better leaving group than OMS, which is a better leaving group. Julie, do you have that list? Or
Yep,
Mubarak?
it's sitting right in front of me. It's CF3 SO3 negative is better than TSO negative is better than MSO negative is better than H2O is better than I negative is better than BR negative is better than CL negative is better than F negative.
Wait, sorry. Okay, so
After
it's better than
H2O is I negative, and then BR negative,
CL.
CL, and F. Yeah.
Yeah. So what I would say from here is to remember that this is like something you need to know for sure. And one thing that you'll notice about these halogens is that it's from there to there, it's exactly the way you would expect it to be, right? It's just the halogens, the more acidic they are, the better leaving groups they are. And then you have H2O. Just remember that H2O is a better leaving group than any of those halogens. And then you have between OTS and OMS, OTS is better, OMS is not so good, which we never really use OMS that much. Just be on the lookout for it if it comes. The one right before that, I don't really think I've seen him use it before that, ever. What is the one right before it?
It was like CF3, and then it's like an OTS with the sulfur. So like it's S, and then there's a double bond O, a double bond O, and then a single bond O negative.
So it's like O3.
Yeah, negative. It's weird.
Okay. So I don't really think I've ever seen him use that. So I wouldn't worry about that one much. But for OTS, OMS, H2O, the halogens, that definitely needs to be known. So now that you know that, you can easily just look at, what's the best leaving group, and you can figure that out from there because you guys know the list now. Okay, so then moving on. Okay, this question is really important, but I think from what I've seen, everyone enjoys this question a lot. So this question is kind of interesting. He'll give you some kind of molecule, and he'll ask you for the, like all the possible places of chlorination or bromination. Let's just say halogenation. So in this example, he gives you this, and he says, what are all the possible places for chlorination? And you have to write each of the products and then indicate which one is the best, which one will have a most stable carbocation intermediate. So the way to approach this is to kind of look at spots that would produce exactly the same thing. So right off the bat, if you see that these two arms, this one and this one, are both very like exactly the same. So since there's nothing different between them, there's no difference between putting a chlorine here or there. They both will produce the same product. Similarly, there's no difference between putting a chlorine, wow, the pencil is very thin. Okay, there's no difference between putting a chlorine here or here. Then you have this other spot is a possible place for chlorination. And finally, the last thing is you have a spot right here. So this molecule has 4 different possible spots for chlorination. Then all you have to do is draw all those possible spots. So I'm going to stick with my colors and just, do them the way that the colors are shown. And then we have red. And then finally green. So those are all of our possible answers. And then he's asking which one is going to have a carbocation intermediate. So we know that tertiary is better than secondary, is better than primary. So this is going to be it. That's going to be the one that's going to have a carbocation intermediate. Now, one thing I'd like to point out is that this second example is a great example of that. It's not like every carbon can take a chlorine, right? Some of them, so this is what it is. Some of them like can't, what do you call it? Some carbons can't take a chlorine. For example, right here, that cannot take a chlorine because it already has its octet filled. So there's nothing there for it to react with and add a chlorine on. Because if we did add a chlorine there, it would look really bad. It would look like this. And this dynamic here of having 5 things attached to the carbon is not stable at all. It wouldn't really remain that way. So we wouldn't get that product really. So when we look at this one, it's important to recognize around the cyclopentane what produces the same product. So these two are actually the same, whether you go to the right or to the left, because there's no difference between them. And this is something that your eyes just have to get used to a little bit. Those two are going to be the same. This is a possible place for chlorination because it has, an available hydrogen there. And then finally, all the places up here. These are all very the same. Whenever you see a Turk group, you know that each of those methyls is going to be the same. So again, this one also has 4 possible chlorinations. So you just write them all out, choose the tertiary one. That's the one that's going to have the most stable carbocation intermediate. He might also turn it around and be like, circle the one that's most likely to react as SN2. In that case, you would choose the primary one. Okay. So I think that's it for this quiz. You guys good?
Yes, but going on to this year's quiz 3, in a similar vein, if he gives us something that's really symmetrical, and I think it was 3 ethyls attached. Yeah. Mm-hmm. Yeah. So I think it should be really important to notice where things are symmetrical. For example, if we had 4 ethyls attached to a carbon, it would then be really important to note that there's really only 2 compounds that can result from that.
So this is really, really important because this has an element of symmetry in it. In that there is no difference between all 3 of these ethyl arms, right? There's nothing to distinguish one from the other. So this actually only has 3 points of chlorination. And I'll show them right here. Everyone assumed that this one was going to be different than these 2 just because these 2 were drawn in a similar way. It's actually the same thing though, because that other one is the same structure. It's just shown a little differently on the piece of paper, but that's not important, how it looks on a piece of paper. So all 3 of the last ones, the last carbons in those ethyl arms are going to be the same. The middle ones are all going to be the same, and then there's one possible point in the middle. Okay.
Yeah. So we all did so badly on this one that I feel very confident that if there's going to be another chlorination bromination question, it's going to be one like that.
Yeah, and I think that the most important part of these quizzes is really for learning. I used to not even study that much for the quizzes because I would only study for the exams. So I wouldn't study specifically for what I think is going to be on the quiz. I would just study for the exam, and then, if I get it, I get it. But because these quizzes are really just a big learning opportunity, they help so, so much. And that's why I really recommend studying these quizzes. I think he draws a lot from the quizzes because they have there's so much stuff there that you might have not seen on your exam, and so it might end up being on the final. So this one is really important, and then the example you gave, Julie, was really good. You said, what about if there had been like 4 ethyls attached to something? So then it might have looked like this. Okay, something like this. Again, you have to recognize that, these are all the same, and then these are all the same. But then what's the difference here, Barca?
There's only 2. Oh,
There's
they're
only
all
2.
same. They're all
They're all the
same.
same, but there's no opportunity to go to the middle one, right?
No.
Because the middle one has already like 4 things attached.
4.
So yeah, so I would definitely be on the lookout for these super symmetrical ones that don't look symmetrical just because of the way they're drawn. But that doesn't really mean anything in this situation because it doesn't really matter about the way it's drawn on a piece of paper. It matters whether it will produce the same product with the same name. Okay, so going back up to the beginning, again, he's just asking like sterically hindered around the alpha carbon, stuff like that. If you have any questions about any of this wording, let me know. And then the second question is about which one cannot be used as a nucleophile. So I feel like you guys are much better at this now because we've learned a lot more about nucleophiles in the last exam. But as you guys know, nucleophiles have to have a lone pair. That's like one of the defining marks. So anytime he asks this question, I would first look for which one doesn't have any lone pairs. And in this case, CH3CH3, that has like no lone pairs at all. There's absolutely no way this cannot be a nucleophile. Like absolutely not in any case. So you need a lone pair. And if you notice, all the other ones have lone pairs there. So they can interact as nucleophiles. It's just that some are going to be better than others. And you guys learned how to recognize this from the trends we noticed about nucleophility going this way and then this way, right? So, next, he has an OH reacting with an NaNH2. And this one is like something we might have forgotten by now for sure. But I will just give like a different example because I don't feel like drawing that whole thing. But it's an OH reacting with NaNH2. So when you see an OH reacting with NaNH2, then what you do is you give this answer, O minus and Na plus. And I'm telling you this is different than the example, which we've done more recently. In exam 3, we did an example that had, let's say it already had like a leaving group. This is the main difference. It had a Br and then it had NaNH3. In this case, it's just substitution. You just put the NH3 on there. Or it was NaN3, right?
I think like these are also really important for exam 3. So if you don't get them in exam 2, exam 3 will become very hard.
Yes, exactly. And I think that this stuff is the hardest part about the final is that it brings it all together. Back when you did exam 2, you didn't even know about substitution this way, right? We didn't really know about substitution in exam 2, right? We were mostly doing mark and anti-mark. So that wasn't even a concern for you. If you saw like an Na and an NH3, then you immediately did this, where it becomes like an O minus, so it becomes like a strong base, right? But the hard part about the final is recognizing all these subtle similarities. These are similar, but the main difference that I will point out is that this is already a leaving group. That is what you'll find is the biggest difference between the way that things can go. If it's already a leaving group, it's going to produce something very different because it's just going to protonate immediately. Another difference is I think, and don't quote me on this, I think this one is an NH3 where you substitute it, and this one is an N3. You can also substitute that. But this is NH2, so it's going to prefer to take a hydrogen to become NH3, which is more stable, and then that becomes an O minus, and the Na plus is going to hover near it in the solution. So yeah. So definitely pay attention to these subtleties. Next, ranking them in terms of reactivity with SN1, that stuff we're already good with, for sure. And just check out the answer key, make sure you can do that. Because it looks like there's 2 options for doing that. And then, what else do we have? A mechanism for SN1 or SN2. This case is SN2. And also the energy diagram. The energy diagram drawn here is very, very good, as is the one in the practice quiz. So if you need to look at your energy diagrams, just check out practice quiz 1 and then quiz 1. Practice quiz 1 has SN1, the energy diagram, and the actual quiz has SN2. And I like both these examples. They're very neat. And then after that, there's just another chlorination question, which I think we're all good with. Okay. Let's move on to quiz 2. So this is practice quiz 2. And here's where we start getting a little bit more into the nitty-gritty of what exam 2 is really about. Exam 2 has a lot of E and Z stuff, but E and Z wasn't even the real focus. The main focus is double bonds and how they can interact via Markovnikov or anti-Markovnikov. So the first question is about E and Z. So I'll just remind you guys how to do E and Z, and I think the second one is a better example. I know there was one that a lot of people messed up on the exam, so when we get to that, I'll definitely do it. So I think this one looks a little bit more complicated. I'm not sure though. But basically, you have to rank them in terms of weight. So this is very similar to what we've done recently with R and S. Don't get confused between R and S and E and Z. E and Z is for double bonds. R and S is for chiral carbons, okay? So neither of these carbons are chiral, right? Because why? Obarka. Why are neither of them chiral? Wait. Okay, Julie, could you go?
Can you hear me?
Oh, Mubaraka, I'm so confused.
Yes.
Okay, go ahead.
Which one are you asking? Because they have two of same things attached to them.
That's actually not
Isn't
why.
double bond the two same things?
No, so the reason is because this is SP3, or sorry, SP2.
Yes. Oh, sorry.
It's SP2 instead of SP3. So in order to have R and S, you have to be able to assign 1, 2, 3, and 4. And they all have to be different weights. So that means you can't have anything exactly the same. So like a chirocarbon, it's gonna have, I don't know, like something we'll call A, something we'll call B, something we'll call C, and something we'll call D, right? So basically you have to be able to have number 1, number 2, number 3, number 4, and they all have to be different weights so that you can rank them in terms of weight. E and Z is very similar because it's about weight, but it's not about chirocarbons, it's about bonds, which do not contain chirocarbons. So we're going to use a similar technique though than what you've been used to with RNS. So by now it should be a lot easier because you're used to like recognizing the heaviest versus the lightest. And the only thing you do with E and Z is you look at each carbon separately and you rank the two things it's attached to, this and this. Rank those in terms of weight. And actually, you're going to start with the carbon closest to it, right? So what's heavier, the carbon on top or the carbon on the bottom, Julie?
Which side? The top one.
The top one. The top one's heavier?
I think bottom is heavier.
Well, the bottom. Oh yeah, the bottom one is heavier. I am so sorry.
Yeah, no, that's fine. Yeah, so the one on the bottom is heavier because this is a carbon that is attached to 3 other carbons. So first of all, usually you can just look at it straight away. Like, let's start with the left actually first. So starting with the left, which I'll do in red, we have a nitrogen and a carbon, right? So we have a carbon here versus a nitrogen here. Which one's heavier? Carbon or nitrogen?
The nitrogen.
Nitrogen's heavier. So we're going to number this as number 1 and this as number 2. Now that's easy. But what about on the right when you have 2 carbons? We're dealing with a carbon versus a carbon. So this is where it gets a little complicated because then you have to look at what that carbon is attached to. So, there's supposed to be another one here. So you have to look at what those carbons are attached to. So this carbon on the bottom is actually attached to 3 other carbons, whereas the carbon at the top is only attached to 2 carbons in effect because it's a double bond. So it's like it's attached to a carbon twice. So if we write this out, it'll look like C is attached to C, C, and H, right? But the bottom one is a C attached to a C, C, and C. So the top one has a hydrogen attached to it and is attached to 2 carbons, whereas the one on the bottom is attached to 3 carbons. So that makes the one on the bottom heavier. So we'll number this as number 1 and this is number 2. Now we look at the way that these are set up. 1 and 1 are opposite from each other. So that means it's going to be E. E means that they're opposite sides. Z means that they're the same sides. Okay. The other one is just the same thing. I think easier though. Yeah, easier. So definitely check that one out. But I'll mention that one again from the exam. I think it was the exam or the quiz where everyone got it wrong. Not everyone, but a lot of people got it wrong. Okay, so, and then we have another one. Here is he's starting to get into elimination. So there's 2 things you need to know from exam 2. You need to learn about elimination a little bit though, not as much as exam 3. You need to know about elimination, and then you need to know about Markovnikov. Like, so basically forming double bonds and then breaking double bonds. So Mark and anti-Mark are both forms of breaking double bonds, whereas elimination is a form of creating a double bond. So they're like opposites of each other. Okay, so the first thing is like he's asking you just for the product. I don't think I need to go through this. No, yeah. Everyone's pretty good with that. The second example is just it's a double bond, which I'll just go like this because I don't really feel like drawing the whole thing, but it's basically this, and there's an H2 with a PT. So remember we said PT, PD, RD, PT, PD, RD. I don't know. There's like a list, but mostly PT and PD he'll use.
I think nickel was in there too.
Nickel,
I don't know which.
Yeah, PT, PD, NI, and RD, I want to say. I don't even know what RD stands for.
Rutherfordium, I think.
What do you say?
I thought it was Rutherfordium. It might also be rhodium.
Oh,
I don't know.
Looking it up, it's rubidium. Rubidium?
Okay.
Yeah, so I'm not that familiar with other stuff on the periodic table. Because this is organic chemistry. We barely deal with anything from the rest of the periodic table. It's just all up in that right corner. So, which is the great part about organic chemistry. So, again, so PT, PD, NI, and RD. So these all create what we said was anti-mark. Now, it's not really anti-mark, but we can just say it's anti-mark to help us remember that it's syn addition. The reason it's not really anti-mark, and if you don't want to hear this, just don't listen, but the reason it's not really anti-mark is because the marker of anti-mark is that hydrogen goes to the place with the least hydrogens. But in these situations, we're substituting 2 hydrogens, right? So this isn't really anti-mark, it's just syn addition. The hydrogens will just go to both sides equally. So essentially what this does is it just takes away your double bond. It just takes it away. But it does add 2 hydrogens, and they will both be in syn addition. But yes, on the regular PT, PD, and NI, RD, they do lead to anti-mark and syn addition. And then remember the opposite was mark and anti-addition. So it's easy to remember those 2 like opposites kind of. Mark is anti-addition, anti-mark is syn addition. Syn addition means that you add them in the same direction, so both have to be going down, both have to be going up. So this is here. So anti-mark, which is syn addition, is can look like both of them going up or both of them going down. That's it. And then we have the opposite of that was mark, which is anti-addition. And that just looks like the opposite. So it can be like, you can either add your Br here and your OH here, or you could do like, I don't know, you could do it the other way. I mean, you could draw them both going in the same direction and just indicate with the arrows. So you could have the Br like this, and the OH like this. I don't know. Either way, you just have to show that one's going up, one's going down. And he doesn't really care about the specifics of everything else. So that's the difference between mark, anti-mark, and mark, syn addition, anti-addition. Then we have a rearrangement question, which I feel like everyone's gotten really, really good at this. It's been very impressive to see you guys come this far. And even on the exam, everyone did really well with rearrangement from what I can remember. So in this, like, as we know, there's two types of rearrangement. There's, we have methyl shifts. And so an example of a methyl shift is, it's usually, you know, like if we have a carbocation here, then what it will look like is the methyl will have to shift over to create a more stable carbocation. So my pencil just died. Yeah. This is ridiculous. I barely ever charge it and stuff. But that's because it like rarely needs to be charged. So anyways, this is an example of a methyl shift, and you'll see in this example that a hydride shift is really not possible. So what I'm talking about is, so this will form, just work on this first. It'll form, so the one methyl shifted over, and the other methyls left here with a positive charge. I remember there's a lot of confusion about why does the positive charge move and how do you know where it moves. And I would just recommend thinking about it on a very like zoomed in level. Like think about it. This used to have no charge, right? Over here. This used to have no charge. We remove one of the methyls. So now it's the same, but it just has one methyl. There's no hydrogens on this one. You can't just assume there's a hydrogen there because there is no hydrogen there. So that means it now has a positive charge. So it's not even a transfer of the positive charge. It's a different positive charge. I mean, it's a different carbon that's positively charged, right? It's not even the transfer of a positive charge. It's more about like the idea that if you take something away from one carbon, that carbon is now going to have a positive charge. And if you add something to the positive charged carbon, then the positive charge goes away. So we used to have a positive charge here. Now that we added a methyl onto that side, the positive charge is gone, right? And then we took away a methyl from this area, so we gain a positive charge. So that's where how to figure out where does the positive charge go. So then let's do another example real quick. I'm gonna just, here's an example with a cyclohexane, because that's, you know, something that we need to be able to see as well. So in the cyclohexane example, it's the same thing, a methyl shift. And all that's gonna happen in this case is we do this, the two things there, and there's a positive charge there. Now, why can't you do a hydride shift in this case? It's because if you look very closely, there's no hydrides, there's no hydrogens to shift on this side, right? There's no hydrogens to shift there. So that's obviously out of the question. There are hydrogens here, there's two of them. But the problem is that shifting them over isn't going to improve anything, and I'll show you how. So if I have a positive charge here and two methyls there, and I see a hydrogen here, and I want to shift it. Sure, you can shift it, but what you'll see is that shifting that hydrogen over is going to produce something where the positive charge is still in a secondary position. So this had no benefit. It went from secondary to secondary. So if you're looking at this situation where you somehow went from secondary to secondary again, or from primary to primary again, or from tertiary to tertiary, if you didn't accomplish anything by shifting it, don't do it. There has to be, you don't do a shift unless there's something to be accomplished by doing it. So and that's why in this situation, hydride shifts are a no-go. But there are some situations where you should do a hydride shift. So when you should do hydride shifts. So usually it'll look something like this, like one methyl next to the carbocation. And so in this case, you do have a hydrogen over here, which you can simply bring over, and what you get is a very nice tertiary carbocation. And the hydrogen is now here on this carbon along with the other one. So essentially it's the positive charge is gone from that area. So those are a few examples of shifts. Here on practice quiz 2, you're given a hydrate shift. It's pretty much the exact example I just showed you. So again, don't shift anything. Don't shift anything unless it accomplishes something. If you didn't accomplish something, you definitely did something wrong. Okay, so this meeting is gonna end in less than 5 minutes. So when it ends, just come back at 5:30. Okay, so next is saying oh, this question I have a feeling I could see this coming up on your exam for sure. So basically he's saying which one has a more stable double bond? Or no. Which one's more stable in general? So when you look at them, basically double bonds, they are what? They create carbons that are what? sp2, sp3, what? The carbon right next to the double bond, like on either end of the double bond. What is it?
sp2, right?
sp2, right? So basically what that looks like, and we'll just zoom into this one for a second. We have a carbon here, and it's double bonded to another carbon. And it has a hydrogen. So this means that it only has 3 areas of electron density. And I went over electron density in yesterday's review. So you can look at that again. So it has 3 areas of electron density, and I explained how you know, but this is going to be sp2. And so sp2 is different than your typical carbon arrangement, which I'll do in this situation. In this situation, you have a carbon attached by a single bond, so that means it has 2 hydrogens on it. This has 4 areas of electron density around the carbon, which means that the carbon is sp3. So now that we know that this is a sp3, right, there's a difference between sp2 and sp3. And you remember that he told you about angles, right? And this is probably the only thing you'll have to remember from Gen Chem specifically. But the angles of
Yes.
sp2 and sp3 are different. sp3 has an optimal angle of what? What is it? Like,
It's 109.5 degrees or something
109.
like that.
Okay. And then what about sp2? sp2 is
Like 120 degrees, right?
yeah, 120. So sp2 has a preferred angle of 120. It is most relaxed when it is a more open angle, so that it can accommodate that double bond kind of. Whereas sp3 can be more narrow because it has more things coming off of it. So the difference is between 120 and 109 degrees. So the fact that here we have a triangle with a double bond in it. Inside of a triangle, you already know the angles inside of a triangle, right? All angles inside of a triangle have to add up to 180, right? Is that correct?
Yes, I believe that's correct.
While. Like, you guys won't believe, like, it was like probably freshman year of high school last time I took actual geometry. But it's, I think all angles inside of a triangle have to add up to 180 degrees. So that means that each one of these is probably around 60 degrees, right? Now, which one is going to have more strain? A carbon that's supposed to be at 109 but is forced into 60, or a carbon that's supposed to be at 120 and is forced into a 60-degree angle? The answer is this one. Because the difference between what it would be most comfortable at and where it is forced into isn't as great as the other one. So double bonds do not like to be put into triangles. It's very, very bad for it. So so if asked the question,
I think like this one was really tricky in particular because you know that sp2 in that formation will be like triangular planar. And you want to think triangles like triangles, but triangles don't like triangles.
Yeah, that's interesting. Yeah, because, well, if you think about it, it's trigonal planar for the actual carbon, not for the entire molecule. But yeah. So, I mean, when I would look at this question, I would explain in terms of, so he asks which one's more stable, but then he asks you to explain. And I think you guys could get this on your final. But basically, I would go into an explanation of the angles, the differences to the. All right. So what were we talking about? Yeah, so if I were you and I saw this question, I would just go into an explanation about SP2 versus SP3, their preferred angles, the optimal angles for SP2 and SP3, and then the actual angle of this triangle, which is 60, and then, and then from there explain why you think one of them is better, more stable. And I would use the word angle strain for sure, which is what answer key did, and I think that's great. Because again, Dr. Saad looks for keywords, and I think he's looking for the word angle strain. He's also probably looking for something about SP2 and SP3. Okay, this one is really, really good, and I feel like I've been getting so many questions about this too recently. We went over it yesterday a little bit, so we'll just go over it one more time. It's about figuring out, so he gives you your molecular formula. So this is question 5 on practice quiz 2. No, practice quiz 4. Yeah. So he gives you the molecular formula, which is C7 H13 Br. He also gave you he also gave you the he gave you what the molecule looks like. And he's asking for what like possible alkyl group with a Br could have eliminated to form this. So the one he gives you is like this. And it has a double bond there. So as you know, elimination is the formation of double bonds. And with bromines, you can have a bromine that protonates and then a beta hydrogen forms double bond with it. So you have to figure out, did the bromine come from the right side, which I'll do in orange, or did it come from the left side, which I will do in green? So all you have to do for this one is you have to draw out each possibility. So I'm going to start with the green on the left. So I'm going to draw out this possibility. Let's say that it had started out with a bromine here. What are the possible places for it to eliminate? Well, as you know, first step is that the bromine is going to protonate. Then something is going to come along. It doesn't really say here what, but something, probably just an O minus, with, I don't know, CH3, is going to come along and it's going to attack beta hydrogens. In this situation, you have 2 beta hydrogens. You have one here and one here. So let's say that the base attacks this beta hydrogen and it formed a double bond. That would give you our desired product, which looks like this. It would give you a double bond here, right? But let's say it reacted with the other beta hydrogen on the other side. So the O minus would come along and it would attack this hydrogen. That would form a double bond here. So if you draw out that product, it has a different double bond. It looks like this. The double bond's here. So this shows us that if our bromine had been in this green position right here, it could have given us 2 products. But he's asking which one gives us the exclusive product shown. So let's go through with the yellow one and see if that one works. So taking this yellow one, if the bromine had been in this position in yellow, right, and our base came along to attack beta hydrogens, where are beta hydrogens? Well, we definitely have a beta hydrogen here. But we actually don't have another beta hydrogen here because that's already, there's no hydrogens there. So what that means is that our base only has one option to attack this beta hydrogen, and that forms a double bond. And what that gives us is it gives us one product only. And that product just so happens to be the exact product we're looking for. So the answer is that this one is the correct one. The bromine had started out in this orange position. So this is the correct one, and this was wrong. So you can draw this with the bromine in the correct position, and then you can just show what I did basically to show that it's the same thing.
I could be wrong, but I think like the answer key did something to show like the top one, like it didn't matter whether you
Oh,
took the hydrogen from the bottom of the triangle or the top of the triangle.
yes. So there's another beta hydrogen here. Like, but it's the same hydrogen because I mean, yeah. So it could also attack from here. I'm just realizing that. Could attack from here and form this double bond as well because there's actually like there's 3 beta carbons, but only 2 beta hydrogens. So that's another possibility, but it's the same thing. Whether you draw it looking like this or the other way, it's the same thing. They're both the same.
Okay, do we need to do that on like the quiz exam to get full credit?
I don't know. I think yes. I think yes. I just forgot that he makes us do that because by now we all know it's the same hydrogen. You know what I mean? But I think he wants us to show that because just to make sure that we're 100% doing right. I would just show it. I would show both of the hydrogens being done, even though they're the exact same hydrogen, exact same product. I would show them both and
Sounds
write that
good.
they're
Yeah,
yeah
they're the same.
they're the same. Yeah. Okay, so then we're going into some cyclohexane stuff. So this question came up again last exam, and it's really, really important. So basically, he says here, he gives us this, and this is the last question on the practice quiz 4. So he shows us this thing going on here, and basically, this is reacting with a base, and yeah, that's it. So then he's asking where, like, draw the product, basically. That's all he's asking. But you might not know this, but it's very, very complicated. So one's first instinct would be to create a double bond here in between the BR, where the BR had been, after the BR protonates, create a double bond between where the BR was and that chert group. Because that follows Zeitz's rule, right? If we went to the other side, that would be against Zeitz's rule. But that's actually wrong. That's all wrong. Because, yes, that's normally right. But when it comes to cyclohexanes, it's a little bit more complicated because we need that 1,3 diaxial repulsion, or the anti-periplanar and the 1,3 diaxial repulsion. We need everything to be axial. That's it. That's what it means, basically. So let's draw this in a chair conformation. That's the only way to actually know. So just do it. Okay. So draw in any chair conformation that works. Anyone that you like. So I like this chair conformation personally. I'm gonna move this all down to another page. What? What is going on? The heck? Okay. So I like this chair conformation, so I'm gonna go ahead and do this one. And all you have to do is you have to put your in an up position, right? So we know that our bromine has to be up. The one thing about the anti-periplanar rule is that your leaving group and your beta hydrogen need to both be axial. They can be up, they can be down, doesn't matter, but they have to be axial. They can't be equatorial. So first, let's just start with our bromine, and that we know has to be axial, like I just said. So bromine has to be axial. And then we're also going to have this up tert group. So if I put this here, it'll just look like that. So it's up, but it has to be equatorial because as we know, this with just this chair conformation, it goes up axial, down axial. So that means that this is up equatorial on the same carbon. So there we have it. That's what it is really. And then after that, we just have to figure out these beta hydrogens. How many like beta hydrogens do we have? Well, we have a beta hydrogen here that's going down. We have a beta hydrogen here that's also going down axial, and then a beta hydrogen that's up equatorial. And this we know just from the patterns of how chair conformations work. So we see that there's actually 2 possible axial hydrogens. So that's great. So that means we could use either one of them. We definitely cannot be using this one, though, the equatorial one. We have to use axial hydrogen. So we can show examples of how each of these axial hydrogens work. So I'll just do the same thing. Up Br, up tert group, equatorial. And in this case, I'll be reacting it with the hydrogen down there. And in the case right above, I'll be reacting it with the hydrogen from here, from the other side. So again, our base just comes along and it attacks this hydrogen, and that forms a double bond. What that gives us is it gives us this with a double bond here. Again, sorry, the bromine had to have protonated first. And then this is just there. And then, so for the next one, for the one on top of that, again, this base attacks the beta hydrogen, and then it forms a double bond. Oh, the bromine had to have protonated first. So our product is going to look like this, a double bond between that spot, and then we have our equatorial tert group there. When you convert this back into cyclohexanes, this one will just look like a double bond, and then, well, actually, a double bond here. Sorry, just a second. Wait, I think I may have. So, when we, so I'm drawing right now the answers, or like the way that they look with the cyclohexanes fully formed. So this one will have the double bond there, and then our tert group is going to be here. Whereas this one is going to form a cyclohexane where the tert group is, it's again here, but the double bond is here. And if you guys remember, I said that we should always show the tert group. Like if there's something that's only sp2, then don't do your stereochemistry there. So that's why I didn't show this as being up, because that's not relevant anymore. Okay, so yeah, I think this is about it. So then after that, we just look at this and we'll see that this one is better because the fact that it follows Zaitz's rule. But the reason you had to do these chair conformations first is because you have to prove that it's even possible to go there, i.e. that there's an axial hydrogen available in that carbon. So anytime you see your cyclohexanes and it's asking about elimination, draw them in a chair conformation to confirm that it's possible. And then if so, which side is it going to go to? Okay. That's it for the practice quiz. Do you guys have any questions?
Not really a question, but like if that tert group had been down stereochemistry, then the double bond would have had to go to the other side, right?
Yes. If we had been looking at it and it had been like this, if it had been a BR that was up and then a down axial tert group, then our beta hydrogens are one hydrogen going up this way and a hydrogen down here and a hydrogen down here. Both of these are not possible. We can't work with those. The only option is this one. So that means that our only product, there's only going to be one product, and it's going to have the double bond going the opposite way of the tert group. So even though this doesn't follow Zaitz's rule, it is our product. Okay. Next. Now looking at the quiz, nothing outstanding really here. The only thing is he goes into a few different reactions as well. So this one is with an OH and H2SO4. So there's a few ways to do elimination. We talked about that. In one of the review sessions, I did this nice little list at the end where we talked about some of the possible ways to do elimination and stuff. But if you have an OH and you want to do elimination, just use H2SO4 or H2O or H3O plus. So H2SO4, it's just going to eliminate this and form a double bond there. I would know this mechanism. You should know all of the random mechanisms that can happen. So this mechanism, we just have O with H, 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 and a plus. So the double bond, the lone pair from here grabs a hydrogen that goes down. Then what we get is we get an H2O in that position. So this is just going to be H2O, which is a good leaving group. And then we have, you can draw that carbocation here if you want. And then basically the OH or the H2O is going to come back and it's going to attack a hydrogen. And that will just go to form a double bond and it'll look like that. And it didn't go to the other side because that would have violated Zaisa's rule. So the double bond has to form in this red position, not this orange position here. Because the orange position, it violates Zaisa's. Next. Okay, then we have a double bond with HCl. That's another like important random mechanism to know. So when I'm reviewing, I would write down all the mechanisms in any of this stuff and memorize them all. Any of the practice quizzes, exams, these are all fair game mechanisms, and you should write them all down. The only one I think he won't ask you that you can definitely probably just not worry about is the free radical mechanism. I have a feeling he won't bring that up. But you can shoot him an email and ask, like, is the free radical mechanism going to be on the final? But other than that, I think you can expect any of these mechanisms and shouldn't be surprised at any of them. So in this one, he's just showing you how a double bond interacts with HCl. So I'm just going to simplify it like the drawing, but you should take a look at it there. So basically, if we look at this, so what happens with the double bond just attacks the H in HCl. So this double bond can just attack. And what happens is that the Cl breaks off. But basically the hydrogen will, in this case, it's going to mark, right? This is mark. Because we don't have like anything in the bottom, like light. There's no light or anything to like tell us that this is going to be anti-mark. So this is definitely going to be marked. So that means that this hydrogen is going to go to the position with the most hydrogens, which means that it's going to go to this end, right? And join the other two hydrogens that were there, leaving a positive charge on this end. So then, after that, all we have to do is we have to show the Cl coming in with its negative charge and attacking that carbocation. And then we just get this. It's just your typical mark. I think everyone already knows like how mark works, that it's going to add, this is just a reaction with HCl and a double bond. So it's going to add a Cl to the place with the least hydrogens and H to the place with the most hydrogens, anti-addition, that kind of stuff. But it's important to kind of understand how the mechanism works. And just, I think the step that most people aren't aware of is how this double bond can attack a hydrogen. People are always confused about that a little bit. Okay. The next thing I'm looking at is pretty much the same thing as what we did before. Right now, again, I'm on the actual quiz from this semester. He gives you a methyl shift. He asks you for a mechanism with elimination. So basically what I did right up here, the same thing again, just show how elimination works with H2SO4 or H3O+. And then finally, he has a chair confirmation one. So in this chair confirmation one, he did do that situation that Julie brought up, where he gave you the same exact thing. It was an up Cl, but instead of a up tert group, it was a down tert group. So when you draw this out, you put your Cl going up. Sorry, just a second. You put your Cl going up, right? And then your tert group is going down. And so that means that you only have an equatorial hydrogen here, and then you have an axial and an equatorial. So it can't react react with is this one, so it'll form a double bond here. So a double bond along this way. And when you draw that out in your chair conformation again, it's the tert group is again, it's still down, but the double bond has formed on the other side of where the Cl had been, away from the tert group. So this is the only one because it has to be anti-periplanar. And remember that word, like that word is so important. That word is that's the golden ticket to actually getting all the credits. You have to write anti-periplanar or anti-coplanar. I don't know. It doesn't seem to matter really. Next, okay. Now we're moving on to the exam, the practice exam. Wait, do you guys have any questions from that quiz?
I think I'm good.
Cool. Looking back at these quizzes, it's really interesting how he just made the same exact quiz, but just everything was like opposite. Like in quiz 3, the practice quiz, he asked you about SN1, but then on your actual quiz, he asked you about SN2. He just switched everything around a little bit, but it's like the exact same questions. Good to know for when you guys move on to Orgo 2. So let's do this. Now I'm moving on to the practice quiz. So he starts off with some naming, which didn't come up in the quizzes, so it's really good that we can practice this now. From exam 2, you just need to be able to know how to name double bonds and alcohols. So again, you have to be able to name double bonds, alcohols, rings, anything, different kinds of branches, that kind of stuff. You need to be able to add your halogens in, know how to name those. Also know the common names. There's 4 of the groups that you need to know: isopropyl, and then there's tert butyl, and then there is isobutyl, I think. I'm not sure, but you have to know all those. Sec-butyl. So there's 4 of them. 4 common names, and then regular IUPAC, including double bonds and alcohols and halogens. So for double bonds, your number 1 has to be in a double bond. So regardless of what else there is going on, if it's a ring, number 1 has to be in the double bond. So let's say I had this one. This is the first one he's given you. So a lot of people might be tempted to make this 1 and this 2 and this 3. But you have to go through the double bond, it's true. But you have to start at the one that's going to have the closest branch to the beginning of it. So if we put 1 here, then we have a methyl already on number 1. So that's better. And then it has to go through the double bond. So you can't just go around this way. You have to go through the double bond. 1 and 2 have to go through the double bond. This is again for cyclohexanes or anything cyclic. 5 and 6. So that's the numbering around there. And then, so we can write this down. We can write that there's a 1 methyl and there's a 6 ethyl. And there is also a 1 ene, right? And there's a cyclohexane or a cyclohexene. Cyclohexene. Okay, so put that all together in alphabetical order. So the ethyl comes first. So it's 6 ethyl and then 1 methyl. And then I've seen people either write it or not write it because it is also implied, like you know that the double bond has to go through the first one. But I've seen some people just write like 1 cyclohexene, but you also don't have to. You can just write cyclohexene. All right. Next, we have an alcohol involved. So alcohols, like no matter what, anything else, alcohols have to be closer to the beginning if there's an alcohol involved. If there's not, then you just try to find the place with the closest branching. So what I mean by this is a really good example. We have a Br here and we have an H here, and then we have a methyl here. You might be tempted to start from this side because if we start from this side, we have a branch coming off at the second carbon. But in reality, you have to start from this side because we have the OH coming off sooner if we start from that side. So when it comes to OHs, you want the OHs to be closer to the beginning of your chain, no matter what. Even if the BR might be closer if you start from the other side. It's important that the OH is closer to the starting side. So that kind of simplifies it though a little bit. So all you have to do is you have to make the number it's closest to the OH. So this is 3, 4, 5, 6, and 7. So we have number 1, we have a 3 all. We have a 5 methyl. We have a 6 bromo. And we have a heptane. Okay. So all we have to do is put that together in alphabetical order. So we'll start with the bromo. So 6 bromo, 5 methyl, and then we have 3 hep, 3 heptanol. Okay, you just put the all at the end of the last thing. Your heptanol is going to be last. Same with the double bond. The ene from the double bond goes last. When you're putting it all together, like everything's in alphabetical order, but ene and all are actually both suffixes to the longest chain, meaning that they just get attached to the end of the longest chain. The word for the longest chain. So heptane is the longest chain, so you just say heptanol. And then cyclohexane was the longest chain in the above one, so you write cyclohexene or cyclohexanol if it had an OH. All right. And I don't think he'll ask you to combine alcohols, and I mean, I don't know, he might, but I don't think he'll ask you to combine alcohols and double bonds. We'll see if they come up. If they do, then we'll see how to do that. Okay, so next he said to draw the bond line structure for Z3-methyl-2-hexene. So again, it just looks like this, and this is a concept you know of now. It's not like we typically do this in IUPAC naming, but if he gives it to you, you should know how to use it. So Z3-methyl-2-hexene. So first of all, we can start with the hexene part. So we know that this is going to be a chain of 6, right? And then we know that the double bond starts at the second one, so we can put a double bond there. And he says that there's also a methyl on the third one. So this is here. There's a methyl there. And then he says that there is a Z conformation around the double bond. So we actually have to go ahead and count this. So we know that there's going to be a hydrogen here, right? So let's count it and determine what's 1, what's 2. So for this one, this is going to be 1, and this is going to be 2. For this side, this one will be 1, this side will be 2. And we need it to be Z, which means on the same side. So all I'm going to do is I'm just going to erase this because we want 2 and 1 to be on the same sides of each other. So I'm just going to erase this and do it like this. So now this is 1 and this is 2. And they're on the same side, right? Both the 2's and both the 1's are on the same side. So that's that. Z3-methyl-2-hexene. Next. Wait, any questions so far?
If for some reason there's more than one double bond in a substance, how do you name it? Do you just like put like the number, comma, the number, and then put the name? Like for example, if there were 2 double bonds in hexene, would it be like 2,5-hexene?
Like, let's say if it looked like this. So I'm not sure about this. Like, I definitely know number 1 it won't come up. But I think I've seen this before. And when you come to the end of it, because this is double bonds starting on the second one and starting on the fourth one, right? The fourth and the second carbon. So I think it might look like 2,4, and then you would say hexene, and then you might also want to add the E and Z parts somehow. I don't know. You might want to add Z or E. I don't know. In between that. But I
Okay.
think that's how it is. But it definitely won't come up.
Yeah, I have not seen it come up so far. That's why I wanted to ask.
Yeah, no. It keeps things pretty simple. Especially on the final, everything you get will be pretty simple. If you've studied well, nothing will be a surprise. Like, seriously, nothing. It is a hard exam, though. For Dr. Son, like, like his finals they're not even hard, but it's very hard to do well on them somehow. So you should really don't underestimate how much time you can put into this exam because it can probably always use a little bit more preparation. Um, it's just like an undergrad, people very rarely would get the full 250 points on the exam. Okay. So here, so now I'm on question 3 of the practice exam, and he's again asking about the exclusive product. We've already shown how to do that. And I would definitely recommend practicing all of these, but when you get the hang of it, it's pretty straightforward. Next, he says, okay, this is pretty interesting. He says, how many products are there for A? And I think we'll just do A. He says 3-methyl hexane. How many how many products can result from the substitution of a chlorine? So chlorination. How many products can result from chlorination of this? He didn't say to draw all of them. He didn't say any of that, so you don't need to worry about that. But basically, we're just going to draw out our bond line structure first. So this is a 3-methyl hexane. So it's hexane, and then it's a 3-methyl, so there's a methyl there, and that's it. So how many spots can there be chlorination for it? Well, this is a very asymmetrical molecule. So we can have one here, we can have one here, we can have, I'm going to run out of colors, one here, one here, one here, one here, and I don't know, one here. Those are all different spots for chlorination. Every single carbon will give you a different product. So if you just count those up, that's 1, 2, 3, 4, 5, 6, 7. So there's 7 possible places for chlorination here. So I would just write 7 next to it. And then try for the second one. The second one is with a, it's 2,2-dimethyl butane. So with 2,2-dimethyl butane, you just start out by drawing your butane, and then there's 2 methyls on the second carbon. And for this one, you'll notice that these 3 are all the same. Again, I said anytime you see that Turk kind of structure, you have to skip this middle one, this one right here. That one can't be chlorinated because it doesn't have enough. The octet is already filled. This is an option, and then this is also an option. So altogether, we have 3 options for this one. Okay, then he has another question about bond angle, and like the same thing. There's a double bond. There's 2 different double bonds. One of them is in a cyclohexane. The other one's in a cyclobutane. So the difference between a cyclohexane and a cyclobutane is that the cyclobutane is going to it's going to have a degree. It's going to be forced into an angle of 90, whereas the cyclohexane is going to be forced into a wider angle. I'm not sure what that angle is again. I know there's a way to figure out the interior angles. Isn't it like
I think it's 120.
Wait, what? Oh, each one is
I think
120?
yeah, maybe. I think it's 120.
120. There's a formula for it. It's There's a formula which I definitely learn every time before one of these finals.
Well, let's see. Let's Google it. The interior angles of polygons is
Yes, n minus 2 times 180. So n minus 2 times 180, and n is the number of sides, I guess.
yeah, I think so.
Sides or corners, whatever you want to call it. It's all the same. So in this case, we have 6 sides. So 6 minus 2 times 180. 6 minus 2 is just 4 times 180. Right? 4. Oh, but that's that's all of them added together, right?
Yeah, and then you divide it by
By
n, which is the number of sides.
Yeah. Divide this by n. So basically what you get is you get 4 times 180, which is, or over n, which over 4, which is basically 180. Because those two 4s cancel out. So each of those angles has to be 180. Wait, is that right? That's right. Yeah.
Yeah,
No,
that's right.
wrong. That's wrong. It's over 6.
Wait, what?
It's over 6. Yeah, I knew there was
Oh,
something
it's
wrong.
6.
Yeah.
It's 6. Okay.
Okay. Yeah. So 4 times 180 over 6, that is 120. Yeah. So what you said originally was right. This has an angle of 120. So the interior of a cyclobutane, each one has an angle of 90, whereas the interior of a cyclohexane, each one has an angle of 120. And just use this formula here if you're trying to explain it. But this person got all the credit without explaining it with that, because like how many of us actually know that formula off the top of our heads? I mean, now you know it, but you know, on an exam you might not have been prepared for that kind of thing. Oh, they did get a point off. Okay. Yes, I think that they could have gotten that point back by showing more angles. Yes, they did get a point off. Okay. So, okay, yeah, so this is basically it. So you can explain how a double bond, right, has carbons that sp2 has an angle of 120 and sp3 has an angle of 109. So you can explain how double bonds create carbons that have sp2 hybridization. And sp2 hybridization likes an angle of 120. But when it's inside of cyclobutane, it's being forced down to an angle of 90. So that creates like a strain, like an angle strain, right? And if you simply put that into a cyclohexane, it's way better because the cyclohexane actually has an angle of 120, so that's perfect. Each corner already has an angle of 120, so it's literally perfect. There's no strain whatsoever. All right, next. We have some E and Z stuff. I guess we can do one of them. Let's do the first one, A. So there's a double bond, has CH2OH, and then it has CH. Oh, there's a double bond O. And then this one has just a methyl, and then NH2. So again, you just look at each side of the double bond, break the double bond in half. Each side, what's 1, what's 2. In this case, on the left, nitrogen is heavier than carbon. So that one is the winner. Then we have, on the right, we have a carbon that's attached to, on the top, we have a carbon that's attached to 2 hydrogens and an oxygen. So it looks like this. Or we'll put the oxygen first. An oxygen and 2 hydrogens. And then at the bottom, we have a carbon that's attached to an oxygen, but twice, because it's a double bond in oxygen. And then 1 hydrogen. So if you look at this, 2 oxygens versus 1 oxygen. This one is number 1. This one's number 2. Therefore, this one is E. Yes, it's E. Okay? And then go through the other examples there as well. Again, we're still on practice exam 2. Next, some stuff about, SN1, SN2, E1, E2. Pink sheet, again, just memorize that. That's just from the pink sheet. Then there's a random question, actually, very random, about the CCC bond angles in a tert-butyl. And so you just need to explain, you need to look at the hybridization and explain that. And the person in this answer key did it very well. Very simple, straightforward. And then this is like something that I 100% can guarantee you will be on your exam. There's some stuff you just know he's gonna put there because it's his favorite question. He always includes it. This is his favorite question. It just has like maybe a K plus, and then an SOCl2, and then a Br2 with light. So in this case with SOCl2, I've also seen him do a PB3, but either way, like it's gonna be pretty much the same. So in the first case, you're just gonna form this like O minus with a K plus. I already showed another example of how you form this O minus K plus or Na plus situation. So the other example I'm just gonna do up here in gray real quick to remind you, it had an OH and then it was with Na NH2. So that gives you an O minus and an Na plus with also an NH3 being formed from that. You don't need to always show that unless he asks for like the two products that are formed. So again, these two are both ways of making it into a very strong base, from like a regular kind of base or not really a base to a strong base. Those are two ways you can do that. Then in the bottom example, SOCl2, as we know, this replaces the OH with a Cl. You don't need to know the mechanism for this. And if it had been, I'm going to do an alternate example on the right. If it had been with PBr3, right, then you just replace that OH with a Br. Okay? And then on the left, we have just Br and light. So Br and light is bromination, which means that you just attach a bromine to the most stable area for a bromine to go. So if you look at this, there's actually only one place that bromines can go. It's to either one of these ends right here. Either one of these ends are all the same. It can't go to this middle carbon here because that one doesn't have like a spot for bromine to go. So we're just going to attach a bromine onto one of them. And that's it. Now, I want to go over this real quick. Remember we said that light favors anti-mark. People always get so confused about light. So there's two different things that light can do. You can have a complete bromination or chlorination, which is like with the free radical mechanism. So let's say you have Cl2 and light. And this is some molecule, it doesn't even have a double bond on it. This means it's chlorination, which means you just attach a chlorine to the most stable carbon there. But if we had a double bond, okay, and this was reacting with Cl2 and light, then it means you attach two Cl's on it. Okay? And it's following anti-mark. Alright, you guys see the difference? Similarly, if we had a double bond with HCl and light, this would mean, again, it's anti-mark. So the H goes to the place with the least hydrogens, and the Cl goes to the other place. All right. Number one, very important to know the difference between Cl2 in light versus HCl in light. Also, the difference between no double bond being there in the first place. That's just a free radical mechanism, chlorination. It's different. This meeting is gonna end soon, so just come straight back in because it's nearly 6:30. So we have 10 more minutes to finish up some other stuff, but this is just something that I've noticed that's important and people mess up on it. Yeah.
What's the stereochemistry of Cl2HV? It's anti, right?
Yes. No.
Okay,
it's anti-mark, so it's syn addition.
Oh, okay, so it's anti-mark, so it's syn.
In addition, yeah. But I just drew it that way, but you should probably draw it the other way. If he asks for stereochemistry, make sure you do it the right way. If he doesn't ask, you can do anything you want. But that's an addition. Light, am I right? Light is one of the markers of anti-mark.
Yes.
For that, yes. Okay. All right, that's it. So this is just something I've noticed a lot of people messing up on. Be careful with that. And then he has decreasing reactivity. That stuff is, that stuff is pretty straightforward. We just, in terms of double bonds, we need to know that a double bond, and this is just Zeitz's rule, which I've explained, like, I can't even count, guys. I can't count. It's been a struggle for everyone to understand Zeitz's rule. But it's just the idea that 4 substituents on a double bond are better than 3 substituents, which is better than just 2 substituents, which is better than just 1 substituent on a double bond. So all you have to do is look at the number of things coming off of the double bond. The maximum is 4. You can have options where there's 3. You can have some options where it's only 2 things coming off, and you can have an option where it's just 1 thing coming off. Just to note, because people are going to ask this, when you watch the recording, you're going to be wondering, this example right here also has 2 substituents. They both have 2 substituents. There's basically 2 options for that. Okay, so again, Zeitz's rule, 4 substituents is better than 3, which is better than 2, which is better than 1. Same, when he asks about reactivity or stability, it's the same thing. This one will be more reactive than this one, Okay. Then he goes on to some reactions. All of these are really important. He has the question number of the practice exam. This is just a list of, it's going to be 40 points in total, around 40 points in total, and it's just like a whole bunch of rapid anti-mark and mark questions. Now, I think there's going to be a few interesting things I want to point out here. So we talked about like double bonds, and when they react with Br2, we said that this adds 2 bromines, right? And it can be either anti or syn addition. Then we said when a double bond reacts with HBr, it adds an H and a Br. So this one's just according to Markovnikov because we don't have any indicators of anti-mark here. So the H is going to go to the side with the most H's, so Br is going to be here. Then the other one that I wanted to bring up from here is a double bond with Br2, but there is H2O in the bottom. So this is going to make it add a Br and an OH. But this is also just going to follow Markovnikov. But in this case, the one that acts like a hydrogen, S+, is going to be Br, and the one that acts like a S- is going to be OH. All right. So that means our Br is going to go here, and our OH is going to go here. Because again, this is just mark. So those are 3 things to point out. The markers of anti-mark, from what I remember, again, I haven't reviewed it all for this, but H2O2, light, PT, PD, whatever. We went through that whole list, Ni, and RD. And is that it? I think that might be it.
Wasn't it like BH3 or like THF?
Oh, B. Oh, THF? Is
Like
that
BH3, like boron stuff, and then there's also like
Yeah.
THF written in my notes.
Okay, yeah. So THF and BH3, or
Which would be like B2H6.
I've also, oh yeah, or B2H6, yeah. All right. So those are our markers, and then also, by the way, this is basically peroxide. So sometimes you'll just write peroxide. So that's the same thing. All right, so going back, after that we have another one. This one's just elimination. So now I'm on 11C. This one's just elimination. So you just form a double bond, and you'll notice that the double bond can only go to one side, not the other. D, also elimination. Remember I mentioned that the only thing you have to do, and this is really important for your retrosynthesis, which you'll get a lot of on the final. The only thing you have to do if you want to eliminate an OH is just do H3O plus. Okay. Then we have another one. Okay, so this is one thing that I remember a lot of people were confused about before. So if you have less than 11 carbons, then you basically make the cis is more stable. Okay. If you have more than 11 carbons, trans is more stable. But this is only within cyclic. For non-cyclic, it's trans. Trans is always more stable. Okay. So again, so if we had a long example, it doesn't really matter whether it has 4 or 5 carbons or whether it has 38 carbons or whatever. Trans is always more stable. But for cyclic, you have a difference of less than 11 carbons and more than 11 carbons. So you just have to count them and make sure. In example E, 11E from the practice exam, we have 6, 7, 8, 9, 10. We have 10 carbons. So that's less than 11. So cis is more stable. If it was more than 11, trans is more stable. All right. Then going on, we have, this is, minutes. Okay. A lot of people miss is the one with 3 O's. So there's ozonization. This is just real quick. I'm going to go over this because I only have like a few minutes left. So we have a double bond, and let's do ozonization. And this basically creates a double bond. No. It's just like this. It just breaks that thing right in half and gives you 2 O's on each side, 2 double bonded O's. If you want to make it look prettier, you should add H's if there's no like methyls there. And then the other option, the other one that involves 3 O's is epoxidation. So that will typically
That's
look
the
like
one that's
this.
weird. As long as
Yeah.
it ends in like CO3, right?
Yes.
So it's anything that ends in like CO3.
They'll have like a CO3H
H.
typically. Yeah.
Yeah.
So this one is epoxidation. That's the difference between this, and it will basically form, and you guys know a little bit more about this from exam 3 when we review for that on Friday. Or no, I can't remember. I think Friday. It's epoxidation. So it'll form like either both of them being up or both of them being down. It's a racemic mixture. Okay. So those are
Okay, so wait. Those are different.
Yes. Wait. Oh, no, they are, let me see. I don't know. Yes, they're different because now we know about RNS that they're different, right? Yes, they're different.
Okay, just making sure. Thank you.
Yes, they're both different because if we had done we could have done something different where it was like the difference between them, because now that we know RNS, if you do RNS, it'll make a difference. But if you had this versus this. You know, those are the same because it's flipped upside down, but these are two different ones. Okay.
Oh, yeah. Okay, that makes sense. Thank
Yes,
you.
yes, yes. Okay. All right, so that is the end of today. So again, we didn't get to go through everything, but going through everything is really hard.